We're actually going to take a break from derivatives here to talk about limits again. We're going to revisit limits using this special theorem called L'Hopital's rule. This is a really nifty theorem that allows us to work with limits that are of indeterminate form. So remember, indeterminate form we looked at, we said 0 over 0 is 1, but we could also have, say, infinity divided by infinity. We don't really know what those look like, but L'Hopital's rule helps us deal with limits that end up in indeterminate form. So suppose that we look at the limit of some function here and we end up with 0 over 0 or plus or minus infinity over plus or minus infinity. Here, this part right here, a can be any real number, positive infinity or negative infinity. A is simply just the number that we're approaching here. So this works for any finite or limit at infinity here. In this case, the limit as x approaches a of f of x divided by g of x, we can rewrite this as f prime of x divided by g prime of x. And actually, whoops, I have a mistake here. This should really say the limit as x approaches a of f prime of x divided by g prime of x. So this is a really nifty tool. It says if you look at a limit and you end up with either 0 over 0 or infinity over infinity, what we can do is we can look at the limit of the derivative of the numerator and the derivative of the denominator. This is actually even simpler than using the quotient rule. Notice I'm just taking the derivative of the numerator and the derivative of the denominator. So this is a really nifty tool. The one thing I will say, you've got to show that your limit ends up in either 0 over 0 or infinity over infinity. If this is not the case, if your limit doesn't look like that, then L'Hopital's rule, this equality doesn't necessarily hold. So it's really important that we double check and make sure that we have a limit of indeterminate form before we continue on. So if I look at this first example, limit as x approaches negative 1, here I have x to the fourth plus x cubed plus 2x plus 2, all divided by x plus 1. I say, let's just try plugging in negative 1. Let's see what happens here. So here, negative 1 to the fourth plus negative 1 to the third plus 2 times negative 1 plus 2 divided by negative 1 plus 1. So my numerator, I should end up with 1 minus 2 plus 2, all over negative 1 plus 1. This ends up being, let me clear some room over here. This ends up being, well, 0. Oops, not 0. It ends up being 0 over 0. So this is, in fact, an indeterminate form. This means I can apply L'Hopital's rule. So, okay, I'm going to look at the limit as x approaches negative 1, so we're still approaching the same x value. I'm just going to take the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator, here I've got 4x to the third plus 3x squared plus 2 divided by my denominator, derivative of x plus 1, that's just going to be 1. And now I say, okay, let's try looking at this limit now. So 4 times negative 1 to the third plus 3 times negative 1 squared plus 2 divided by 1. Here I should end up with negative 4 plus 3 plus 2 over 1. This is, let's see, 1 over 1. 5 minus 4 would be 1 over 1, which is just 1. So that means this is my limit. So rather than having to rely on factoring, and actually we probably could have, just looking at this, we probably could have factored that numerator. We don't have to necessarily fall back to factoring here. Now if we end up with this 0 over 0 or infinity over infinity, I have this tool that I can use that will kind of expedite the process. It'll speed up the process of evaluating these types of limits. So let's look at a few more examples. Here I have the limit as x approaches 0. I have e to the x minus 1 divided by x squared plus 3x. So be careful here, because when I look at this, I'm going to try and plug in 0. So this is e to the 0, e to the 0 minus 1 divided by 0 squared plus 3 times 0. My numerator is 1 minus 1. My denominator 0 plus 0, so I have 0 over 0. So this is an indeterminate form. I've made sure of it. So let's go ahead and make sure to apply L'Hopital's rule now. So I want the limit as x approaches 0. Here we're going to take the derivative of the numerator, so the derivative of e to the x minus 1, that's just e to the x. And the derivative of my denominator here would be 2x plus 3. And I'm going to try to plug 0 in once more. E to the 0 divided by 2 times 0 plus 3. Here I have 1 over 0 plus 3 gives me 1/3. This is my limit. So it's a really, really nice theorem. And again, I will say, please make sure that you're checking that your limit is indeterminate form first. It ends up as 0 over 0 or infinity over infinity. Some of the problems that I include on quizzes and exams and some of the problems that are in my math lab will not be indeterminate form. They'll just be, say, 0 over 1. In which case L'Hopital's rule doesn't, you don't even need L'Hopital's rule in that case. You would just end up with 0. So be careful. Make sure that you're double checking that. I want to look at a few more examples though. Here I've got this big long example. I have limit as x approaches 2. I have x cubed minus 3x squared plus 4 divided by x to the 4th minus 4x cubed plus 7x squared plus 12x plus 12. All right, so well, let's try plugging this in, and I feel like I'm going to need some more room, so I'm just going to jump up here. So let's see, this is 2 to the 3rd minus 3 times 2 squared plus 4 divided by 2 to the 4th plus 4 times 2 cubed plus 7 times 2 squared plus 12 times 2 plus 12. And here you'll want to double check in my numerator. Let's see, I'll end up with 8 minus, this will be minus 12 plus 4. In my denominator, I've got 16 plus, oh boy, I'm going to run out of room here, aren't I? Let me make some more room. So here we'll end up with 8 minus, we said that was 12 plus 4 all over 16. Plus 4 times 2 to the 3rd. 2 to the 3rd would be 8 times 4 would be 32. Plus, let's see, 28. Oh, you know what I did? I missed a minus sign, didn't I? Here, let me fix this right now. Here, this minus sign right here, I forgot to include in my answer. So let me fix that right here. This should really be minus 32, plus 28, plus 12 times 2, I've got 24, plus 12. In my numerator, let's look. 8 minus 12 would be negative 4, plus 4, I have 0 in my numerator. In my denominator, 16 minus 32, plus 28, plus 24, plus 12. Here I have 48. To be honest, I believe this is a typo on my part because I had anticipated to show you a case that didn't actually work out, but that's okay. Here we end up with 0 over 48. 0 over 48 is not indeterminate form. This is actually just 0. So please make sure that you're checking this. If you had gone to take the derivative of the numerator and take the derivative of the denominator right away, you would have gotten the wrong answer. So just make sure that you are showing that you end up with indeterminate form first when you try to evaluate that limit. Let's look at one more example here. This one's pretty tricky, so we'll take our time with it. It says limit as x approaches 0 from the right-hand side of natural log of x divided by cosecant of x. And for this, one thing I'll just clear up here, L'Hopital's rule does work for one-sided limits. So this does work for one-sided limits, which means we can use L'Hopital's rule just like we would for a two-sided limit. Now, if I look at the, and I'm going to break this up here, if I were to look at the limit as x approaches 0 from the right-hand side of natural log of x, that is equal to negative infinity. If you were to look at the graph, and I can actually just graph it really quickly, graph of natural log of x looks something like this, where I have this vertical asymptote right here at 0. We're approaching negative infinity. So I know that that's what my numerator looks like. In my denominator, if I were to look at the limit as x approaches 0 from the right of cosecant x, this is not a function we deal with all the time, but if you were to look at cosecant of x from the right-hand side of 0, you would see, well, something like this, where we have yet another vertical asymptote at 0. This time we are approaching positive infinity. So I end up with negative infinity divided by positive infinity. This is another indeterminate form. So okay, we've shown that this is indeterminate. Let's apply L'Hopital's rule. So let's say, limit as x approaches 0 from the right-hand side. I'm going to take the derivative of natural log of x, that is 1 over x, divided by derivative of cosecant of x. The derivative of cosecant of x is negative cosecant x times cotangent x. And this is kind of ugly to work with. My suggestion to you at this point would be to simplify this, to kind of clean this up. We're dealing with cosecant and cotangent. I don't particularly like working with those functions if I can avoid it. So I would probably take a moment and I would rewrite this as limit as x approaches 0 from the right-hand side. I'm going to leave the numerators 1 over x for right now. In my denominator, I have negative 1 over sine of x times cotangent of x. That's cosine x over sine of x. So let's see, I'm going to actually just simplify my numerator right here. Sine of x times sine of x, that's really just, let's say, sine squared x, and then negative 1 times cosine, that'll just be, how about negative cosine? So I'm going to, rather than divide these two fractions, we can multiply by the reciprocal. Once I do that, I'll have limit as x approaches 0 from the right-hand side. I should end up with, I'm going to put the negative sign right up front, negative sine squared x divided by x times cosine of x. So it's a little bit of work to simplify it, but if you leave it here, I have tried this problem without simplifying, you end up in this really ugly loop where you actually just get stuck in an indeterminate form and you have to kind of simplify it another way in order to get out of it. So this is a way that works. I promise we are going somewhere. But if you're ever in doubt, I always take my trig functions and break them down into terms of sine and cosine, and I think that usually solves a lot of your problems if you're unsure where to go when simplifying. So okay, cool. I have this limit. Let's try to evaluate it here. I will have negative sine squared of 0 divided by 0 times cosine of 0. Negative sine squared of 0, that's just going to be negative 0, or just 0. And here I have 0 times 1. I have 0 over 0. Well, shoot. We ended up with another indeterminate form. That's not so good. So I want to use L'Hopital's rule again. There's nothing to say that I can't use L'Hopital's rule more than once, and in fact, that was kind of the anticipated result in the last one. Maybe I'll go back and make another video to show that. But here, I ended up with infinity over infinity, so we use L'Hopital's rule. Here I'm ending up with 0 over 0 for my limit. I can simply just, well, maybe not so simply, but I can just use L'Hopital's rule again. We said L'Hopital's rule works for 0 over 0 or infinity over infinity. So I want to take the derivative of my numerator and of my denominator. Just to clear things up, I'm going to put that negative sign right there with sine of x. And remember negative sine squared x? Remember this part right here? Maybe it would be helpful to rewrite that as, oops, I don't want to do that. It would be helpful to rewrite that as negative sine of x squared, so that when we go to take the derivative, it's a little bit more obvious that, oh, we're going to have to use the chain rule here. So, okay, I'm using L'Hopital's rule because I ended up with 0 over 0. I would like to look at the limit as x approaches 0 from the right-hand side. I'm thinking about, for my numerator, I'm thinking about this guy right here. So I do need to use the chain rule. This will look like negative 2 times sine of x to the first power times the derivative of the inside part, that'll be cosine of x, divided by, in my denominator, I have another problem here. I have x times cosine of x. This is a product rule problem. So I'm going to take the derivative of x, that's just 1, times cosine of x, plus, this time I leave x alone, derivative of cosine of x, that's negative sine of x. And let's just maybe clean this up now. This is limit as x approaches 0 from the right-hand side, negative 2 sine x cosine x divided by cosine x minus x sine x. Okay, so I have a limit. I've simplified it using L'Hopital's rule. Let's try evaluating this limit one more time. Let's see if it works. So here, we're just going to plug 0 in and hope for the best at this point. Negative 2 times sine of 0 times cosine of 0 divided by cosine of 0 minus 0 times sine of 0. So in my numerator, I'll have negative 2. Sine of 0 is 0. Cosine of 0 is 1. Cosine of 0 is 1 minus 0 times 0. So I end up with 0 divided by 1 minus 0. 0 divided by 1 gives me a final answer. Oh boy, not of 1. I almost messed up the last step. Of 0. 0 divided by 1 is simply just 0. So you will see these types of problems from time to time where you need to use L'Hopital's rule more than once. And again, it's really, really critical to show that you end up with that indeterminate form of 0 over 0 or infinity over infinity. If we're not showing that, you do not know that L'Hopital's rule is going to apply, you very well could just crash and burn on that problem because you're using L'Hopital's rule when it doesn't even work. So just be careful that you're showing that you end up with 0 over 0 or infinity over infinity before you apply L'Hopital's rule.